Okay, so we are going to be looking at 3D vector pathways. So in National 5, we have done those some 2D vector pathways. So just as a wee example, if I've got the vector from A to B, I can get from point A to point B in that straight line, or I could get to that vector from A to B in any kind of length of ways. So as long as the arrows go in the same direction, so they like follow along, I can go in any roundabout way I want, using as many points or as few as I like to get from A to B. So from this example, we can say that AB is equal to so I go from A to C, and then I go from C to D, and then I add from D to E, and then I add the vector from E to F, and then I add the vector from F to B. Okay, and this works in 3 dimensions as well. And it's just saying that when we add all those up, it's going to give us the equivalent of from A to B. The thing to be careful of is the arrows need to be in the same directions. So if, for example, I've got a square and I've got a vector like this and a vector like that, we know it's a square or a rectangle perhaps. And we've got A, B, C, and D. If I want to go from C to A, right, because it's a cuboid of some description, or cube of some description even, it's not a cuboid, it's two-dimensional. So because we've got a cube, we can say that we know that this distance from A to D is the same as from B to C. But remember, vectors aren't taking into account where you start, it's just the directions to get from one point to another. And to get from point A to point D, you have to do the same thing you have to do to get from point B to point C. So we can say from here, we know that so AD is the same as from B to C because of the properties of a cube. Right, and we also know, same to do with the cube or any form of rectangle. We know to go from A to B is the same as going from D to C, like the size and the direction are the same. The starting point isn't, but the size and the direction of that distance is the same. So A to B is equal to D to C. And that's just knowing that in a cube that the sides are parallel and the same length. Okay, which we should have known for a long time by now. So then we can say from C to A, what we're going to do to go from C to A is we've got to go from C to B, and then from B to A. So C to A is equal to C to B, add B to A. Right, but we don't have C to B, we've got B to C. But we know that going from C to B is just the reverse of going from B to C. And with vectors, that means it's the negative. So we've got negative B to C plus, same from B to A, is the reverse of going from A to B, so it's the negative of going from A to B. So from C to A is negative BC, take away AB. Okay, so it's kind of just looking at the directions and the pathways. So we're going to go on and do a couple of examples of these in 3 dimensions, looking at the most common 3D shapes we're going to see. Right, so the first one we're most likely to see is a cuboid of some description. Sometimes it's a cube, sometimes it's a cuboid. So from here, first thing is that I'm going to ask to find a resultant vector for A to G. Right? So, we're starting at A and we're working our way to G. There's lots of different ways we can do this. And again, we're going to be relying on some of our knowledge of our vectors and our shapes. Right, so first of all, we can't just go diagonally there. We've got to follow along the sides to get to some way we know. So the first bit of our journey can be to go from A to B. Right? So any side that is parallel to that, or so like A to B and D to C are the same vector. The starting point is different, but the vector to get from one point to the other is the same. It's also the case because of the properties of a cuboid that E to F and H to J, H to G are also that same vector A to B. So like all of the ones that I'm about to do a little blue arrow on are the same vector. So all of these have the exact same kind of instructions to get from one point to the other. Okay? So A to B is all of those. Right, so then if we keep following, we're probably going to want to go from B to C along there. So this vector here, which other vector have we got in our diagram that's the same? Well, that's A to D. But we've also got F to G and E to H. Right, so we're going from A to B, and then I've got to add from B to C. And then our last one, to get from C to G to get us to where we're wanting to go. It's this last one, the green one, right? And the ones that are the same as those are B to F, so any of the ones kind of going up that direction are the same vector to get from those points because we've got a cuboid. And we know that in a cuboid that a lot of our shapes are the same, like our sides are parallel and that the lengths are the same. Okay, so that's why this works. So then we can add C to G. Okay, we can get these with numbers and things as well, but for the cuboid, that is all we're going to do. So we're going to go on now to look at the next shape that we might see. Okay, so this time we've got a rectangular based pyramid. So we've got the rectangular based pyramid, and we have been given for this one that A to B is equal to 3, 7, 4. A to D is equal to -2, 3, 1. And that A to E is 7, 3, -9. Okay? So, we want to find, this time, a pathway from E to C. Right? So, this time we're going to start by kind of drawing our pathway and figuring it out on the diagram. So we're starting at E. So if we start at E, we're going to trying to get to C, which is over. So we're starting here, and we're trying to get to here. We can't just go down this way. We don't know the size of that vector. Right, so we're going to have to kind of go the long way round, which is how vector pathways kind of work, going the long way round. So we don't know this one, we don't know that one, so we're going to have to choose the one we want. Because we're going in the opposite direction of the arrow, that means we've got to take away. So we're going the opposite way, down this way. I'm going to use green, right? So we're going there. So that's equal to take away A to E, right? Because we're, instead of going from E to A, that's the same as taking away A to E. Okay? So we're going kind of following down this way. And then the next bit we're going to do, doesn't matter, there's two different ways we can do this, right? So we can then go from A to B, that works, following this way along the bottom. So then we're going to add A to B, and then our last one to go this way, follow this one that way, is so then we add B to C. So from this point we can then do our vector addition. So negative A to E, so we just change the signs on them, so we get -7, we get 3, -3, and we get +9. So the signs have all just flipped to being the other way. AB is 3, 7, 4, and D is -2, 3, 1. So then we get -7 plus 3 is -4, take away 2 is -6, and then we've got -3 plus 7, which is 4, plus another 3, which is 7, and then we've got 9 plus 4 plus 1, which is 14. So we found the vector pathway from E to C. Okay, so going on to our last question. Right, so we're on to our last shape. This one is a more interesting one. And this one is called a parallelepiped. So it's a 3D shape that has been made by taking a parallelogram and stretching it into being a 3D shape. So it's kind of like you've taken a parallelogram is like you've taken a rectangle and kind of squished it a bit. This is like we've taken a cube and squished it a bit. Okay, so those PQRS is one side of the parallelogram, and then it's been stretched backwards or forwards depending on kind of how you see things. Okay, don't worry too much about spelling parallelepiped. Okay. Or being able to say it, to be honest. It's not too big a deal. Right, so for this one we are going to do that we have a point here, which we're going to call X, which is halfway in between W and V. And we're going to go from P to X. So we're doing P to X, that's what we're trying to find. Okay, so let's start off by starting at P and we'll go our route to find it. So this time I'm going to go from P, I'm going to work my way backwards, and I'm going to go towards T. So it's equal to P to T, and then from T I'm going to go up to W, so plus T to W, and then I'm going to go halfway along, so plus half of W to V. Okay? So now if we get some kind of sizes for these vectors, so if we have that, PQ is equal to -4I plus 6J plus 10K. Okay, so we can get these in unit vector form. P to T, we're going to say that one is 3I minus 2J minus 3K, and P to S is equal to 7I plus J minus 5K. Okay? So we can go from there. Over here though, we've not got P, T, P, Q and PS. We've not got all of them. We've got some of them, but not all of them as they are there. So P to T is quite an easy one. So we know that one already. So that is 3 minus 2 minus 3. Remember, we can just change it into component form really easily. So T to W, we've got there, T to W. That is the same as this one, and this one. So all of those lines have the same vector going in this direction. So the one we've been given, that's one of those, is P to S. So we can add p to s, which is 7, 1, minus 5. Okay, and then we've got from w to v, so this line here, we're going along there. That is the same as from t to u, and from s to r, and also the one we've been given, which is p to q. Okay, so we're finding halfway along there, so that means we've got to add a half of p to q, which is minus 4, 6, 10. So we sort out that half first, so we get 3 minus 2 minus 3, plus 7, 1 minus 5, plus, and then we've got half all of these, so we get minus 2, we get 3, and we get 5. And then we add them all together to get our answer, which is going to give us p to x. So 3 plus 7 is 10, take away 2 is 8. Minus 2 plus 1 is minus 1. Add another 3 gives us to 2. And then we've got minus 3, take away another 5, which is minus 8. Add 5 is minus 3. So from p to x, that's saying you have to go 8 in the x direction, 2 in the y direction, and minus 3 in the z direction. Because we got given these as unit vectors originally, generally you tend to leave it in the form you get given it in. So it would be 8i plus 2j minus 3k. Okay, so that's it for 3D vector pathways. If you've got any questions, leave a comment or ask in class if you're lucky enough to be in my class. Okay, that's this for vector pathways.